kind of handed these out last time. Anyone need the trig identity sets? Two more. 3 more. No. The other thing that I'm going to hand out is review material for that midterm. The way I printed it, the font is very small. If that's going to bother you and be a problem for you, then just like come by my office sometime. I'll switch it bigger. I just noticed once I wrote down enough problems that I'd like on kind of overbought on how many problems we wanted in this review packet. And so I didn't want to actually print out 10 pages. If you do look at that thing, most of the problems in there are problems you know how to do. If you just keep looking through there until you get to the section called trig identities, it's all stuff that we do. And then after that, there's a section called angle addition and then doubled angles. Other than that, you know how to do everything in there. So, let's do some things then. Let's talk about trig identities. So let's start with this. There's like a word I've used a few times, a word identity. Right, like the Pythagorean identity. What does it mean? What does the word identity mean in that context? What's special about the Pythagorean identity that it's called an identity? Cool, let's even start with this. What does the Pythagorean identity say? Yeah. Nice. You started with sine. Sine squared, and I'll give the name to a name to the input. Sine squared of theta plus cosine squared theta equals 1. And I'm going to add this. No matter what you plug in for theta, that equation is true. So that's what an identity is. So an identity is an equation that's true no matter what inputs you plug in. So like, we know some of those. Here's a flash from the past. If I multiply two things inside of a log, what is that the same as? Adding the logs together. Here's an example of an identity. An identity is an equation that's just always true. And you know why these are useful, right? They let you simplify some things. So, let's list some other identities we know. If I ask you to write tangent in terms of sine and cosine, what would you tell me? Tangent is the same as? Sine over cosine? Nice. That's an identity. No matter what angle you plug in, tangent of theta is equal to sine theta over cosine theta. I guess maybe no matter what is a stretch. Are there some inputs that you just can't plug into either side there? Yeah, right. Cosine better not be 0. So I'm not, like, pi over 2 would be bad to plug in. We know other versions of that. How about cotangent? Cosine over sine. Cosecant is 1 over cosine theta. Cosecant is 1 over sine theta. We have some identities that say that some trig functions are either even or odd. Let's write those down. So let's start with cosine. Is cosine even or odd or neither? If you don't just know this, let's think about how you would check. Let's say I ask you this as a test question. The final exam is only one question, true or false, cosine is even. And you don't want a 50-50 chance whether you pass the class. How do you answer that question? How do you figure it out? What is it? How can you tell if the function's even? If the graph reflects over the y-axis. So let's generate a graph for cosine. We could do it by hand, but let's not. There's the graph of cosine x. That look even? Nice. So cosine is even. And I did phrase that in terms of like an exam question because that's a perfectly valid strategy. If there's something you don't remember, a fact you don't remember on a test, but you do know how to figure out whether that fact is true or not, do that. And since cosine is even, what can I do with a negative sign inside of a cosine? So even functions are functions that behave like x squared. What can I do with a negative sign inside of a squared? Just get rid of it. If you see an even function, you can drop the negative. Cosine of negative theta is the same as cosine of theta. There's another identity. That's a fact that's true no matter what angle you plug in. How about sine? Even or odd? Odd. And what can you do with a negative sign inside of an odd function? You can pull it out front. So sine of negative theta is the same as negative sine theta. And how about tangent? How many people have a graphing calculator on them? If you don't just remember whether the tangent's even or odd, right, it'll take a quick second, but I think it's a second that's worthwhile. And I guess whenever you're graphing a trig function, if you want a meaningful graph, make sure you're in radian mode. So take a look. Even, odd, neither, both. How do you tell if a function is odd? What does the graph of an odd function do? Symmetric over the origin. So if you like take your calculator screen and rotate it 180 degrees around the origin, do you get the same graph back? Cool. So is it odd? Nice. Tangent is odd. So there's another identity. When you plug a negative into tangent, you just pull that negative out front. We also had some identities that told us what happened when you add pi over 2 to an angle. Now let's just see how many people just remember. What's the cosine of theta plus pi over 2? Yeah, say it louder though. I hear a sine. Do I hear something else? Negative sign. Well, since I've heard two options, let's test. And let's test by looking at a graph. Like the graph of sine? Except it's negative. So, cosine of theta plus pi over 2 is exactly the same as negative sine theta. And now that that's written down, does that like
at least feel familiar, like something we did a while ago when we talked about symmetries? Yeah, corresponds to adding 90 to rotating by an extra 90 degrees. Yeah, that makes the x value become negative and turns it into the y value. How about sine of theta plus pi over 2? Any intuition? I hear a negative cosine. Do I hear a second for negative cosine? Do I hear an alternative? Does that look like negative cosine? No, it just looks like cosine, right? Sine of pi over 2 plus theta is the exact same as cosine of theta. And instead of looking at a graph or tangent, let's like reinvent it on the spot unless you just remember. Anyone just remember what the tangent of theta plus pi over 2 is? Could we figure it out then? And doing this will be a trick that I'll use an awful lot as today progresses. Let's try to figure out what, I'll switch colors, tangent of theta plus pi over 2 is. And this is a strategy we've used a few times, so let's see if you just come up with it on the spot. If you wanted to figure that out, what would you want to do? I know what to do for sine and cosine, right? If that tangent were a sine, I already have the answer right now. So let's try to write that tangent in terms of sine and cosine. What is tangent in terms of sine and cosine? Sine over cosine. So I won't do anything with that input yet. I'll leave it alone. I'll replace that tangent by sine theta plus pi over 2 divided by cosine of theta plus pi over 2. And let's see what we can do with that. What's the sine of theta plus pi over 2? Cosine theta is apparently what's written down already. What's the cosine of theta plus pi over 2? Negative sine theta. Ooh. Let's see, there's a negative and it's just in the denominator, so let's pull it out front. And now I see cosine over sine. What is cosine over sine? Cotangent. Tangent of theta plus pi over 2 is negative cotangent theta. There's another identity. In fact, we have a proof of that one now. It's just scrawled off to the side. So here's the game that I want to play today. We have all of these trig identities. And we've used them an awful lot, right? Like if you want to solve a trig equation, an important step is going to be using a bunch of identities to solve some stuff. So let's do exactly that. So let's prove new trig identities. And a key point of today is when you're trying to convince someone that some equation is true, you really want to have an argument that's well explained. No step should feel mysterious. They should all be laid out in detail. Let's try to prove this trig identity. 1 minus tangent squared x divided by sine x minus sine x tangent x. I claim that that is equal to tangent x plus 1 all over sine x. And so in some sense, you might read this as follows. I'm telling you, this side simplifies to that. And now I'm asking you to do the alphabet to do that simplification. And I'm going to go to the next page because there's like some guidance in how to do it. Let's try to follow along some steps. So a good strategy to prove a trig identity is to pick a side that looks more complicated. This equation happens to have a side that obviously looks more complicated. And try to simplify it. So 1 minus tangent x divided by sine x. Well, the side that looks more complicated. Maybe I'll put the goal up on top.
inside. Do you see anything there in that? Look, there's a bit of guidance there. Apparently there's some stuff with factors. Do you see any factoring that looks useful? So here's one way to try to proceed.
So I want to like turn this side into that side. So let's look at this side. I certainly see a bunch of signs in the denominator, right? In fact, does everything in the denominator have a sign next to it? Oh, that's exactly the situation when you can factor out a sign. So let's factor the denominator by factoring out a sign. When I factor out the sign, I'm left with 1 minus tangent x.
That feel pretty okay? And that even gives me an idea of what else should happen. In this thing that I wanted to simplify down to, that 1 minus tangent x goes away. So that means this 1 minus tangent x, it should cancel with something else, hopefully something in the numerator. So let's try to factor that numerator. How does the numerator factor?
Excellent. It factors as 1 minus tangent x times 1 plus tangent x. And here's like the callback to a fact that this should make you think of. So how did you know that that should factor that way? Yeah, cool. Yeah, that's exactly what factoring is. You're like anti-foiling. So you want two things that multiply together to be 1 minus tangent theta. Well, I guess that means the first term better be 1, because 1 times 1 is 1. Tangent times tangent is tangent squared, and you need to be negative, so one should be positive, one should be negative. And then you just see if it works out by foiling. And in general, this always works. Here's a fact. The difference of squares formula says that whenever you see a difference of two perfect squares, that always factors as a minus b, a plus b. And that's exactly what happened here. 1 is a perfect square. Tangent squared is a perfect square. So it factors.
All right, neato. So we've done the factoring. And what I would be perfectly happy seeing in the write-up is all you're doing there is factoring. So that line is true by factoring. Now that we've factored, do you see anything that cancels? Anything shared to the numerator and denominator? The 1 minus tangent looks like it'll cancel. Let's cancel them. By canceling, this looks like we wind up with 1 plus tan x in the numerator divided by sine x in the denominator. All right. Is that what I wanted to simplify it down to? Cool. That's the whole story in this proof. This identity is true because you can factor out and you can cancel. Nice. So let's think about other things you can do. You also know all of the identities that you already know. You know the Pythagorean identity is true. You know cosine is even. You know sine is odd. You can appeal to any of those facts when you're proving a new identity. And here's one that will use some of the identities we already have. Here's an identity that I claim is true. Tangent of x times cosecant of x is equal to secant of x. All right. So let's try to go through a decision-making process. Is one side of that equation obviously more complicated than the other? Yeah, one side has two things multiplied together, the other side is just one thing. I mean, not every equation has an obvious more complicated side, but when there is an obviously more complicated side, consider starting with that. No promises that it'll always work out, but it's a place to begin. So let's start with tangent of x times cosecant of x and try to see why that simplifies to just secant of x. So, what do you see that seems useful?
Right. Tangent of x is sine over cosine.
Nice. So let's express everything in terms of sine and cosine, since tangent x equals sine x over cosine x. And I guess we should do the same thing with cosecant. What is cosecant the same as? Flip to the previous page if you need to know what I'm talking.
1 over sine.
It is 1 over sine. All right, so let's use that. This becomes sine x over cosine x times 1 over sine x. And maybe even just ignore the guidance to the side. Take a look at that. What seems like a good next step? What would you want to do to that next? Cool. I don't like the word cross multiply there because like cross multiply to me says that like you have a fraction equals a fraction, and you're like moving the denominators to the top. But like, describe to me what you mean by that. Because you probably have like the right. What would you want to write as the next line?
1 over cosine.
Just 1 over cosine. So really, you're canceling some things. I see a thing in the numerator and that same thing in the denominator, and it's all multiplied together. So we can cancel. In fact, we can be more explicit than just canceling by canceling the sign of x's. That being said, like if in your horrible description you wrote by cross multiplying and had that as your next step, I'd probably be okay. I might like write the comment that it's not usually what's meant by cross multiplying, but I'd be okay with that. Cool. All right. So let's keep on going. Tell me about what you would want to do next.
I'll write 1 over cosine. Oh.
Yeah. So, yeah, I've already written 1 over cosine. So what's special about 1 over cosine? What can I do with that? It's the same as secant. Oh, so we're actually just like done. We can express that in terms of secant. We get secant x. And so taking the more complicated side, we simplified it down to the simpler side. Nice. So when you're asked to prove a trig identity, this is the type of stuff you're being asked to do. To explain algebraically, or using other things, why the more complicated side is the same as the simpler side, or why the two sides are equal at all, while explaining every step. And that I want to emphasize. I want to see explanations for every step in your write-ups. So let's do one more. Here's an identity that is often called a Pythagorean identity. There are really like 3 Pythagorean identities. There's sine squared plus cosine squared equals 1. There's tangent squared plus 1 equals secant squared, and another that appears on the bottom of the page. Let's try to prove this identity. And maybe I'll see how people feel. Should I just be quiet for a bit? People want me to keep talking? Nice, then I will. So, tangent squared plus 1 equals secant squared. Is there one side that looks obviously more complicated? I mean, that's all qualitative, so even if you disagree with me, that's fine. Tangent squared plus 1 has a plus. The other one is just one thing. Let's start with the side that has a plus, with the idea that if you start with the more complicated side, there's space to simplify. So let's start with tangent squared plus 1 and see what we can do. What seems like a reasonable plan of attack? So when in doubt, like I don't see any moves right now. But I do see trig functions other than sine and cosine. Could I express all these in terms of sine and cosine? What do you get when you do express everything in terms of sine and cosine? fraction squared is sine over cosine squared. Nice. And I think I'm going to be slightly off script, so I'm going to cross that off. So let's just write down the things that get used. Since tangent equals sine over cosine. And I think I want to do more things in the same line.
What else would you want to do with that? Let's get a common denominator. I guess before I do that, from what's written, like let's put that square in the numerator and denominator. Because how do you square a fraction?
You get it into the numerator and denominator. So that's sine squared theta over cosine squared theta. By getting common denominator. And that common denominator, I guess, is going to be cosine squared. So how should I rewrite that 1?
Or cosine squared over cosine squared.
Perfect. And the only reason to ever get a common denominator is so you can add or subtract fractions. So whenever you get a common denominator, the next command had better be add those fractions. Let's add those fractions. What do you get?
Sine squared theta plus cosine squared theta over cosine squared theta plus cosine squared theta.
Almost. Once you have a common denominator, you just add the numerators.
Right, like 1 over 2 plus 3 over 2 is just 1 plus 3 over 2. All right, so, but now we find ourselves stuck again. Like we did all the algebra. Whenever you see a fraction plus a thing, that should make you excited. There are some obvious steps to do. Get a common denominator, add the fractions. But now that we've done that, we need to look for something to do next. Anything you see? The top equals 1 because of the Pythagorean identity.
So by the Pythagorean identity, maybe I'll even put a comma here. Sine squared theta plus cosine squared theta equals 1. That means I can replace the numerator of this fraction with 1 because it's equal to 1. All right,
Giving me 1 over cosine squared theta. Nice. Cosine is 1 over cosine is secant. There's a square, so I guess that's secant squared.
express everything in terms of secant, getting you down to secant squared theta.
All right. Does that example feel pretty okay? All right. So, the next thing I would like to have you do is you do one. There's one at the bottom of this page. I haven't given you space to do it. So, as a consequence, you'll need to just take out some blank paper, try to come up with a proof of the identity that I just wrote. Anyone want me to just hand him some blank paper? I'll have you pass this down. All right. I'm quite proud of myself there. I managed to tear out that many pieces of paper without any, like, shredding on the top. As a bit of guidance, the identity that I'm asking you to prove at the bottom of the page, does it look pretty similar to the identity that you just proved? Maybe you could follow some similar steps. This isn't like a test or anything. You can like insult each other. Do more. yourselves in a situation where you're stuck and want a little bit of guidance, like to come around, just raise your hand. If anyone's in a situation where they have like a write-up that they want me to just look at, give them some comments, raise your hand, I can look at that too. Let's come together.
So I saw some things that looked reasonable. So let's try to prove this identity.
Anyone come up with a proof? All right. Let's start with the first step. So what was the first thing you did?
Cotangent is cosine over sine. So let's start with the more complicated side. Cotangent squared theta plus 1. Let's rewrite that as cosine squared theta over sine squared theta. Nice.
All right. That agree with most people's first step? Anyone do anything wildly different? All right. That makes sense. Like, there's not that many false moves that seem sensible here. That's not to say there aren't other false moves, but I think that was pretty good. All right. What did someone do next? Yeah.
You can rewrite the 1 as sine squared over.
Oh, wait, I lost the plus 1. Rewrite 1 as sine squared over sine squared. I'm going to put the thetas in. So this becomes cosine squared theta divided by sine squared theta plus sine squared theta over sine squared theta. That's not the only way to describe either of those steps in words. I just want a formal description that tells me what you did. There's more than one way to put those into words. All right, what next? Add those fractions. The whole reason to get a common denominator is to add fractions. So let's add fractions, giving me cosine squared theta plus sine squared theta all over sine squared theta.
All right. What do people do next? Or, if you didn't make it farther than this, what seems useful now? Yeah. That top equals 1.
So let's use cosine squared theta plus sine squared theta equals 1 to turn this into 1 over sine squared theta.
All right. Are we almost done? Yeah. And I'd like, as you start doing proof of an identity, you don't necessarily need to see all of the steps. Just like following a nose makes some simplification. You might wind up making your life worse instead of better, but then you can just go back to where you started if you decide to like reset it. Once you get to a place like this, you're you can see how to get to the end point. What do you do next?
Rewrite it as cosecant squared.
Nice. And that completes the proof.
I wanted to get down to cosecant squared, and I did. Nice. I feel. So here's the takeaway. When you're asked to prove a trig identity, you're being asked to simplify an expression. but you're also told what the goal of the simplification is. You want to show that that thing is equal to the other thing, and each step needs some explanation just to make sure everything's going to check out. So let's do one last of these. We've got time.
Here's an identity. Cosine alpha divided by 1 minus sine alpha equals 1 plus sine alpha divided by cosine alpha. So in the past couple examples, the first question was like, let's start with the side that looks obviously more complicated. Is there a side that looks obviously more complicated? No. So like, there's no good way to decide which side to start with. And so on the bottom of the page, there's like the second strategy that's useful in this situation. Well, let's just follow the current steps. Do this real fast. So let's just pick a side to start with. Which side would you want to start with to do the simplifying? Sure. Let's start with 1 plus sine alpha divided by cosine alpha.
And at a glance, maybe it doesn't look like there's anything super obvious to do. But you can use the fact that you have a goal in mind to try to come up with something to do.
I want to make that thing look more like this thing.
So what's something on the right-hand side that like is different from on the left-hand side? There's a cosine of A in the denominator.
Let's just try to, as opposed to the numerator over here. So let's just try to force a cosine of A to show up in the numerator. Let's do that, I guess, by multiplying and dividing by cosine of A. So let's do that. Let's multiply and divide by cosine alpha, and let's just see what happens. So I'll see 1 plus sine alpha divided by cosine alpha all over cosine alpha over cosine alpha. And you might be super tempted to say, aha, I see a cosine of alpha in the numerator and the denominator. I can cancel. That would be like a silly step, right? Because it would just be undoing what we just accomplished. So let's try to do something other than that. So you take a look at that. Let's just take that and simplify it. We don't want to cancel that cosine from the numerator or denominator. We want to take advantage of it. So what do you see here that looks like it might be useful? Or what do you see here, period? What's something you could do? Let's multiply some fractions together. And I guess there's some like boiling you need to do, but yeah, whatever. Let's multiply these fractions. So to multiply fractions, you just multiply the numerator and multiply the denominator. So it looks like the denominator is cosine squared alpha. The numerator is cosine alpha plus cosine alpha sine alpha. And I'm not worried whether like that's a helpful step. It's just a step that I could do. And let's keep in mind the goal. There's the goal. So there's what I have. There's what I'd like to get. What's something you notice that's like different between these two that we might be able to try to use for some guidance? It's like, we got the cosine on top, but there should also be like a 1 minus sine alpha on bottom. So let's try to see if we can take this denominator and turn it into something that has a sine in it. How do you get a cosine squared to turn into something that has some sines? Oh yeah, that's true. That's true, but it's not what I want to do. What does the Pythagorean identity say? Nice, and this is like off to the side. Could I use that to get cosine squared in terms of sine squared? Yeah, so let's do that. So grammatically, I think bi doesn't make sense, since cosine squared alpha equals 1 minus sine squared alpha. This is going to become cosine alpha plus cosine alpha sine alpha, all over 1 minus sine squared alpha.
All right. So that's a little bit better. I at least see like a sign in the denominator. But I see too many signs. I see a squared instead of degree 1. Maybe that means if I like do some factoring and some canceling, I'll get what I want. So, do you see any factoring to do?
So on one side. And then
Nice, yeah. So the numerator, how about we can get 1 has the cosine next to it? Let's use that. How does the denominator factor? Hint. Difference of squares formula? Is the denominator a perfect square minus a perfect square? There's something you should notice. Squares show up an awful lot when you use things like the Pythagorean identity. So perfect differences of squares will often show up. Let's try to use that.
Using the difference of squares formula, how does 1 minus sine squared alpha factor?
1 minus sine squared alpha, 1 plus sine squared, or 1,
Yeah, but fewer squares.
yeah, so that's,
By factoring, and maybe I'll even add this difference of squares.
All right. And I guess another space, but I'm not really out of space. There's another space. This space button on the line. See anything that looks useful now? What do you see? Yeah.
There's the goal. I see the cosine. I see the 1 minus sine. What's left? Oh, 1 plus sine divided by 1 plus sine. Those cancel. By canceling the 1 plus sine alphas, we get cosine alpha divided by 1 minus sine alpha.
Cool. So notice, at basically no point did I like know how this was going to go until it was already done. You start with an identity that you believe should be true. As long as you keep doing correct algebra, you keep finding more things that are equal to the thing you started with, eventually you got to get down to the thing that you wanted to get. That feel pretty all right? So,
I don't have enough time to start in on the next example. Instead, let's try to now optimize this proof. So here's one observation that maybe I make. It looks like to get this, I like distributed the cosine alpha over the 1 plus sine alpha. And then eventually I factored it back out again. Do you think I could have just like not done the first one? Yeah. So here's one modification I'll make because I see that this proof could have been simpler. 1 plus sine alpha cosine alpha. 1 plus sine alpha cosine alpha. Just don't do the distribution.
cool. All right. So, with that done, here is what I'll ask you to do over the weekend. So I know I've given you plenty. There's like lots of work to do. You have some like open-endeds that are coming up on you. Try to take some time and look through the rest of this section of the notes. There will be a ton more quick identities this week. I'll spend some time tomorrow thinking about more of those quick identities. And then I'd like to move on to a bit of a proof quiz afterwards. So, have an idea about how do you come up with the proof of a twig identity? How do you explain a proof of a twig identity? Oh, maybe I'll ask this question as people are packing. So the twig identity that I had you prove, did anyone like write down a bunch of mathematical steps and then didn't write down any lots? Cool. If you do that on the homework, you get like 50% max. It's like, add some sentences. I want the sentences. I really want them on the proof of twig identity. Even if everything looks perfect and correct, but you haven't written down any lots, 50%. Does it give you a picture, or are you supposed to like draw the picture on your own?
You're supposed to draw a picture.
All right.
Thank you.
Thank you.
It uses like angle of depression, angle of elevation.
Yeah.
So I was getting confused, like how I'm supposed to draw the picture of like where the angles and lengths go.
Nice. So you're measuring all of these angles based on yourself.
Yeah.
So you're standing here, you have like this, these things that measure what angle you're looking at. And it's telling you whether you're looking up by some distance, if it's an angle of elevation, or down, if it's an angle of depression.
Okay.
And it looks like there is a class in here. So, do you have time to like walk us up?
Section's over.
Yeah.
I feel like your class is at this time now.
All right, let's head
I'm actually watching
upstairs.
this.
You want to talk about some stuff too?
Yeah. Can you email her and be like,
Oh, yeah. I have my office hour at 1 o'clock.
And that's till 10. I mean, what else do you
Until closer to 1:50 because I am covering someone else's class right after my office hour.
Good, you're running early. It's Friday, it's Friday.
Okay. If you don't, then if you can show up at my office at like. So from 2 to 2:50, I'll be covering this class. So.
My bio exam at that
15
time.
hours?
It's like
Wait, at 30 is your bio exam?
It is when you're in management.
Oh, 2 to 2:50, I think anyway. If you can come
So,
right
when I
after
went to the back, I was like,
I'll have some time.
you guys want to give me like
Okay,
a day off or something?
Cool. Try to make my actual office hour, but if you can't do that, do the other thing instead.
Go on vacation.
Yeah.